simplest circuits that implement logic operators. And whenever we'll learn one logic gate, this is the thing that we should learn about it. The first one is what is it? Operators with the name or the logic gate, the circuit notation or visual notation, so that you see that on the design, you know what it is. Okay? In visual form, that you don't have to read the name. Next one is, you may say again, why do we need visual form? Because we need let's say it support or aid the visual design, so it's easier to wire your circuit. Next one is the input-output definition. You'll have the text definition or human readable definition about text requirement. It's going to write in English description or other languages. Say what is the input, what is the output. Then the next one is the truth table. Is another way of giving the input-output definitions, or whatever combination of the inputs are, what is the output. So that one is a truth table that we have learned. Or another way of expressing the input-output relationships is using Boolean equation. So we'll use Boolean algebra, like we have seen before. What kind of operator we use to combine inputs, and correspondingly, what kind of output do we have? So there are three main ways of specifying input-output definition like this. Actually, for every circuit, we should have several more. Let's say you have timing specification as well, but we don't focus on timing over here. So now, the first circuit gate that we going logic gate that we will learn over here is the NOT gate. So visual notation is like this. This one is visual notation. It has the input A, and this one is a visual notation, and it has the output Y. Now, the text definition of this one is Y is true if A is false and is false otherwise. And this one is exactly the definition of the NOT operator inside proposition logic that we already studied. And the truth table is specified this way: if A is true, Y is going to be false. If A is false, Y is going to be true. And the math expression of this is going to be written as Y equal to bar of A. So we create a new knowledge from the existing knowledge, or we have a new bit from existing bit, because we're creating new thing. This one is computation. Then the next one is the buffer logic gates. So it has this visual design. It's going to be like this: A, then the buffer, and then Y. And for this one, it is actually Y has the same values as A, or it simply buffers the input, you may see. So Y is the same as A. Why do we need to use this one? So sometimes we use it for delaying the signal transmission a bit for time synchronization purposes. Now the truth table is, Y is having the same values as A. So we're going to write Y equal to A for the Boolean algebra part. Again, this one is visual notation or operation. This one is description in English about what does it do, what's the relationship between the input and output. This one is the truth table, which is a combination of all the possible input. Then you'll have the output. Then this one is Boolean algebra way of writing the same thing. You may have the question again, why do we need to know this? Because in the future, you want to use a circuit, you need to know what does the circuit do for you. The next operators that we learn is the AND operators, logic gate, which is to implement the AND operators. And its visual form gonna be like this. And the human description of this is exactly the same as the AND logic operator. Y is true only both A and B are true and false otherwise. And this one is a truth table, and I highlight this area. Y is true if only both A and B are true. And we'll be written them as Y equal to AB together, or sometimes people put a dot for the AND operator. Okay, so they sometimes call them as a product operator. Now, the next logic gates that we learn is to implement the OR logical operator. So for this one, its visual notation is like this. Okay, so in human specification will be Y is false only when both A and B are false. It's true otherwise. So its input output truth table specification gonna be like this. The red color is here. It's easier for you to remember. And this one is gonna be written in Boolean algebra as Y equal to A plus B. Okay, so this one is written as plus B in Boolean algebra. Okay, now the next operators logic gates we'll learn is to implement the XOR logical operator, or this one is explicit OR, and its notation is the same as the OR, but you don't have another line over here. Okay, and it is the same definition as the XOR logic operators, of course. So Y is true only when A and B are different. Okay, so when only A and B are different, then Y is true, all the rest will be false. And it is written, which is Y equal to X, A XOR B like this. Now the next logic gate is the NAND logic gates, or to implement the NAND logic operators. So this one is actually not AND or negative version of the AND. So we will have the AND first. And whenever you see this little circle over here, which means that you negate the output of that. So the NAND is defined as Y is false only when both A and B are false. So it's a negative version of the AND. So you will see this one, it is a negative version of the AND. It's become false in here and it become true in everywhere else. And it is going to be written by A, B, the negative version of it. So it's going to be A dot B, sometimes the negative version of it. This one is a NAND gate. The next one is the NOR gate, which is very similar to the NAND gate, which is negative version of the OR. So wherever the OR is true, it's become false, and vice versa. So wherever it is false right now, it is true. Okay, so this one. Okay. Then it can be written as negative version of A or B. So you negate the output, you get the negative version of that. Okay. So the next version is the negative version of XOR. So it is called XNOR. So we'll have the definition this way, and you'll have the it is false when A and B are different. So you'll see the differences here, and the math expression of that is the negative version of X of A XOR B. So as we mentioned earlier, circuit may have multiple input gates. Let's say they may have n input AND gate. Let's say for an example, we can have operator N3. So they have 3 inputs instead of 2 inputs. Okay. 3 is just an example. We can have more than 3. And for this one, it is true when all the inputs are true. So that is the only case. Okay? This is only true when all the inputs are true. And because we have 3 of them, so the possible combination of the inputs gonna be huge, which is 2 power 3 won't be 8 of the possible combination. However, it is true only for one case, which is all the inputs are true. Okay, so that one is in truth table specification. Now we can write them as Y equal to ABC, or sometimes we'll write A dot B dot C. Okay. Very similar, we can have the multiple input gates for the OR gate, or we can name them as OR3. It's gonna be the OR operators, but actually with 3 like this. Okay. Then the definition again is it's only false where all inputs are false. So it's gonna have its truth table specification this way, and the math expression is A plus B and plus C. So far we have learned all the basic logic gates, which is the simplest physical component which is used to implement some logical operators to create new knowledge. But computer is not that simple. They don't work with individual bits. They work with the whole sequence of bits and computation. So how do we combine this logic gates in order to perform more complicated computation? And that one is we're going to produce more complicated circuits. That's why we'll learn about circuits in the next part.